in mid-February is always a bit of an assumption of risk, but I think we sort of drew an inside straight here, so we're excited about that, and we're excited to see you all here. We are here to talk about the potential intersection of artificial intelligence and advancement, because AI is coming whether we are ready or not. In fact, it's probably safe to say that AI is already here. It's not weird anymore to talk about self-driving cars. It's not bizarre when you upload a photo to Facebook and Facebook knows who's in the photo and suggests that you might want to tag them. My kids spend a crazy number of hours trying to get Siri and Alexa to say words that they're not allowed to say. This is something that is out there and shaping the world that we're working and living in. So in advancement, we may not have felt AI yet, but it's coming. And it may be 6 months, it may be 2 years, it may be 5 years. Feel it, we will. Many of us in this room may not know much about AI yet, but now over a decade into the digital revolution that has changed so much about the way that we live and work, we have learned some things about how to deal with impending change. First off, we know that it's much better to meet the change in a proactive and informed way than it is to pretend it's not happening or to close your eyes and hope that it goes away. That didn't work for social media, it didn't work for crowdfunding, it didn't work for giving days, and it's not going to work for AI. Second, we know that if we decide that we are going to take the initiative and wrap our heads around what's coming, it's more efficient, it's more effective, and it's more fun to do it with a community of other people who are interested in the same topics and grappling with the same issues. Some of those people might be staff at your own institutions or other institutions. Some of them may work at the tech companies that work in this space. Some might be consultants. Some might be interested people who don't really have any sort of natural alignment with any of the organizations active here. But it's really important to have all of these perspectives at the table because we really need both the technical perspective and the business perspective to begin to figure this out. This type of community with regard to AI and advancement probably would evolve organically over the next 12 to 18 months because it has to. But what we're hoping to do today is we're hoping to accelerate that process based on what we've learned about how we as a profession learn. So we have in this room the nucleus of a community of people who care about the potential of applying AI to a particular set of business problems that are endemic to the various different program areas that we're going to break up into workshops to discuss this afternoon. And what we're hoping to do is to kick off a conversation that is going to last long past the conclusion of today's program and position us to really engage with this in a productive and proactive way in the future. So to start things off on the right foot, I'm really proud now to introduce Martha Pollack, Cornell's 14th president. President Pollack has been at Cornell for almost a year now, having served previously as the provost at the University of Michigan. She's a computer scientist with research expertise in artificial intelligence, including natural language processing, automated planning, temporal reasoning, and constraint satisfaction. And we're really grateful that she's made time in her busy schedule to spend a few minutes with us this morning. Please join me in extending a warm welcome to President Martha Pollack.
Hi, everybody. I want to thank Andrew and I want to thank Case for sponsoring this today. I get asked to say hello to a lot of different events on campus, welcome a lot of different conferences and programs, but of course, given my own background in AI, I was particularly happy to be able to come to this one. You know, the digital revolution didn't start a decade ago. It started decades ago, decades and decades ago. I myself spent more than a quarter of a century actively doing research and teaching on AI. As Andrew mentioned, I started in natural language processing, trying to get computers to speak languages like English or Japanese or Swahili or what have you. I worked on automated planning, trying to get computers where you could tell them what you wanted to do and not all the steps to get there. I worked on temporal reasoning constraint optimization, which I won't try to explain in 10 seconds. And what I also worked on was a very applied project, which had to do with using AI techniques to design technology that could help people with cognitive impairment. And the reason I mentioned that is people said, what? Computer science can do what? AI can do what? And you know, I think people now maybe sometimes feel the same way about their own field. Like, what's the connection between AI and advancement? Well, AI and its sister fields of data science and machine learning really today, at least on campuses, at universities, are in just about every discipline. There's almost not a single discipline that hasn't been influenced by these techniques, and I think the same thing is happening in industry. And one thing you folks have going for you is that AI is not going to supplant advancement. There are disciplines, there are industries, there are fields where I think 5, 10, 20 years, the timeline varies, but at some point in the future, those workers are going to be replaced, and we're going to have a dislocation, and we're going to have to deal with that. And I think automated driving is the prime example of that. But what you do is based on human relationships. That's not going away. But I do think, I firmly believe that AI can help you enormously in finding the relationships and tracking the relationships and seeing what the trends are in all kinds of ways. So I am just really excited that you all came to Cornell, which has a fabulous set of faculty working in AI, and I hope you have a very productive and educational day. Thanks.
All right, thank you, President Pollack, for those remarks. I'm sort of feeling inclined to go charge a castle now, thinking about the potential here. So now we're getting into the meat of our program, and I want to take a minute to talk you through how we've structured today. To start with, I want to acknowledge very explicitly that there are a large number of people in the room who are complete beginners or novices, and I include myself in that group. To the others in this group, don't worry. The point of this exercise is to learn together. And don't forget what I said a few minutes ago about needing both the technical perspective and the business perspective to be able to get somewhere in this conversation. You're all subject matters in your respective program areas, and that's really important. To those of you who do bring the expertise to the table, I ask that you be patient with the rest of us and help us wrap our heads around what we are engaging with, some of us for the first time. So conversations. This is a conversation. Conversations are more effective when everybody is on the same page about what they're talking about. This morning is intended to be sort of a crash course in AI. What is it? Where did it come from? Where is it going? Why is it popping now? And we're going to start off with an overview of the basics from David Schmoys, getting ourselves oriented and establishing some commonality in terms of fundamental concepts and vocabulary. After that, we'll hear from our industry panel and dive a little bit deeper into some of the key questions and examples. Over lunch, Adam Martell is going to start narrowing our focus to the use of AI in advancement specifically, and that's going to set the stage for our workshops in the afternoon, when we're going to break up into our program area workshops and try to apply what we've learned this morning to the problems, the frustrations, the challenges, and the opportunities that we see in our daily work. So let's go ahead and get started. We're about to hear from David Schmoys. David is the Lade Atkinson Professor of Business Management, Leadership Studies in the School of Operations Research and Information Engineering here at Cornell. He received his PhD in computer science from the University of California at Berkeley, and he held a faculty position at MIT before joining the Cornell faculty. You can find a detailed description of his research interests on the conference website. But given the role that we've asked him to play for us this morning, putting us through sort of an AI boot camp, I really want to highlight his skill as a teacher. He has received multiple Excellence in Teaching Awards from the Cornell College of Engineering. David, thank you so much for spending time with us this morning, and we are now in your hands.
It's a pleasure to be here. First of all, the mic is working. You can all hear? Good. Good lighting. You can see the slides. So it's a great honor to be able to have this opportunity to give you a brief intro, what was dubbed as AI 101. Really, this is Cornell, so we have 4-digit numbers, so it's not 101, it's 1001. And before I get started, I want to give thanks. I've stolen quite a number of slides from my colleague in computer science, Killian Weinberger, who is advancing many of the subfields that I'll be talking about today. But let me just start by grounding you with thinking about headlines. So these are all within the last year. Barely a day goes by when one leading publication or another doesn't talk about the impact of AI, and as Martha already mentioned, its sort of sister fields of data science and machine learning, on having an impact on day-to-day lives. And this is part of a wave that's happening. And what I want to do today is a number of things. First of all, what I'd like to do is just give you, and I talk about AI and data science, and I talk about machine learning. What exactly do I mean? So just some high-level, big, broad brushstrokes. These are different disciplines. They have different meanings, and yet they overlap in all kinds of ways. And sort of understanding which pieces of which tools and what perspectives will intersect your professional lives comes from a brief understanding of just the basics there. I'll also give some broad brushstrokes of a brief history of AI and also of data science and to some extent machine learning, though Martha already did because her career epitomizes in many ways the history of AI. Then I'll spend a little bit of time, why now? So why has the world evolved to the point that this is the confluence of events that's bringing it to the forefront at this juncture in time? And then I'll spend a little bit of time, I won't get too technical, but I want to give you some sense of the technologies underneath it and what we do or don't understand about those technologies. And I'll maybe say some brief thoughts about my own perspectives on how what I've set things up for intersect what it means to be doing alumni affairs and development. And then I really hope that I'll have structured things that we have lots of time that I can attempt to answer your questions. And probably I won't be able to, and I'll just have to say, I'll have to check on that and there, but I really want to leave lots of time for questions. Okay? So that's the game plan. And another ground rule, okay, I am a teacher. I won't call on you to answer questions, but I do want to take questions along the way. So if something I say doesn't make sense, please, raise a hand and let's have this also be a dialogue. Okay? So those are the ground rules. What is artificial intelligence? What is AI? And to some extent, this picture, though it doesn't project perhaps so well, shows that there are really two axes to think about it, with sort of as a result 4 different things that it could think about it answering. It could be think science of making machines that think like humans, act like humans, think rationally, or act rationally. So notice that in the horizontal lines, we're sort of making a dichotomy of, are we building machines that mimic human behavior, or versus are we building machines that instead are rational, rule-based, model-based, following entities that actually capture, maybe in some sense, the best aspects of what it means to be human. So that's the horizontal axis. And the vertical axis says, are we actually thinking about cognition? Are we thinking about thinking? Or are we thinking about the results of cognition? Are we thinking about actions? And this underlies 2 philosophical differences of really what goals should be. And the questions of what is at the essence of AI, of which of those 4 perspectives, which of those 4 philosophical endpoints are we aiming for, has really been at the core of questions driving different movements within AI since its inception more than 50 years ago. And yes, Martha talked about a few decades. AI's roots really go to the 50s, and we'll talk about that. Okay. So that sort of some brief figure. Now, in contrast, and this wasn't so visible in the blurbs leading up to it, there's this other emerging wave in data science. So what exactly do I mean by data science? It's not clear yet. It's an earlier stage of development, but it's talking about the confluence of a number of technological advances that have driven the need for better science. And what are those advances? Well, one is that we're all aware that the increasing extent to there is a digital record of life on Earth as we interact with it. What your phone carries, what what your email carries. There is a record of life that is being collected and live streamed as I speak. Now, going along with that is the growing computational power in order to process the enormous quantity of data. And this is increasing at an enormous rate. And then beyond that, there is an increasing effectiveness of what I'll call computational statistical tools that allow us to represent, analyze high-dimensional data, to forecast based on it, and to help guide decision-making. And to have a broad impact across a wide range of disciplines. You need only think about using Waze on your phone to tell you how to go as to think about a product of what data science can and should be across a wide range of things. And this goes hand in hand, although data science is perhaps the name that's winning. There's another sort of buzzword name that's out there, that of a interplay of analytics. And there are shades of difference, but these two kinds of evolutions are closely aligned. And aligned with and underneath as a key mover and driver for both of these initiatives is machine learning. And machine learning itself can be viewed as a subfield of computer science that sort of the one-line thing is to think about computers that actually learn the algorithms that are being executed rather than being constructed by an expert programming in advance directly. And I'll give some examples to that. But now I say I've set the frame for those three different swaths of intellectual domains. And now I'm going to spend a little bit of time talking about each and how they evolve. Okay, so first, a short history of AI. And to show you I really mean it, any questions? So AI really started with the birth of the computer in the modern digital age. It really started in the 40s and 50s. From my perspective, there was a Boolean circuit model of the brain, of sort of thinking about it in 43. But in some sense, the founding moment of artificial intelligence was a classic paper of Alan Turing, entitled Computing Machinery and Intelligence. Now, this is the same Turing that designed the Enigma, that broke the codes that you all saw the movie. He also invented the theory of what it means to be a mathematical object of a computer and what it means to be computable. And as yet another contribution, this amazing man also sort of defined one of those philosophical pieces of artificial intelligence, of what we all call today the Turing test. And that is that if you can have a conversation with a computer with being unable to distinguish whether you're having a conversation with a computer or having a conversation with a machine, with a person. And so this really was sort of the founding moment of artificial intelligence, dating to AI. And you're used to this thing in your pocket that's a phone. A computer in Alan Turing's day was a room-filling object that you interacted with by one phase handing a program and then computing and then some period of time, lengthy period of time, getting an answer back. And to foresee the kind of question there, I can't begin to think about what it means to be projecting the future in an entirely different level. So that set things off. From the 50s to the 70s, there was a lot of excitement. I mean, machines were becoming faster. They were being more powerful. They were able to compute broader things. There was a fantastic, you read now from sort of the documents, there was a fantastic meeting in Dartmouth in '56 of all the people who set the agenda and that's really where artificial intelligence got rolling as a thing to do, as a discipline of computer science. There were some initial developments in the 60s, and it was really a sense that, hey, this is the brave new world, and we can solve everything. You read quotes from that time, they think that by 20 years ago, everything would have been solved. Didn't quite work out that way. The 70s and 80s can be sort of framed in terms of what we might call knowledge-based approaches, that they were building using the storage capability of a computer to build a corpus of knowledge that could then reason. And this sort of went to the rationality piece and the dimension that I mentioned, rather than the human piece. And little by little, while there were short-term advances, that knowledge, the expert system was a guiding and useful tool, it was very clear that this was different from intelligence. And you know, for better or worse, AI has lived with the fact that it's called artificial intelligence, and we all have a very human resonance with what that actually means. And this evolved into a period of time which might be called AI winter. But then starting in the late 80s, there was a resurgence of AI, and this is in many ways driven by this one piece in machine learning, which took a statistical approach, which built on a foundation of a probability notion of uncertainty, of a way of characterizing likelihoods and beliefs that captured a more human piece of that. And then this started to have impact. And there was also this sense of notions of agents that interacted. And again, it was sort of a dimension of moving from the rule-based rationality piece to the sort of more performance and deliverables and human piece. So that's a brief history of AI, sort of how things going. And notice I sort of ended at the quarter century that Martha alluded to that just sort of kicked things off. Data science is much more brief in terms of where it is, but I wanted to give you a hint that it also has really early roots. And in some sense, a formative paper in data science is an amazing article of Vannevar Bush of As We May Think, which outlined a concept that's not so different from the World Wide Web as we use it today. Again, in a world before we had computers that were at all the flavor and the interactability that we've come to take as part of our daily lives. And it foresaw all kinds of questions that we now have grappled with and in many cases solved. As I think about data science and those tools, there were many elements that really all computer technology came of age in the 50s to the 70s, underlying all kinds of things. Salton, here at Cornell, had a great smart system for information retrieval. I mean, it's one thing to use the computer as a storage mechanism, but it's only useful if you have a way of interacting with it to get the information that you need. The whole notion of networking. We take for granted that email comes from one end of the world to the other, but there are computer networks underlying it, and there were technological advances that built us to the point that we're there. All of this was there. And then sort of the commercial aspect. And in many ways, I think of American Airlines as being the pioneer of taking a lot of this kind of concept and with their Sabre system of having a distributed interactive means for all the reservations and the tracking of transactions that made a major airline run at that point. And that really showed as a forefront of what the technology could bring. But again, parallel to this, there was the statistical foundations. Tukey in '62 published a really transformative article, The Future of Data Analysis, that really talked about how data can inform decisions and be not just a forecasting tool, but a decision basis for decisions. And this was his larger work, Exploratory Data Analysis, 15 years later. And the interplay with computing was highlighted by the fact that the main statistical institution, the ISI, founded a section in highlighting computational work already back in the late 70s. But then the transformative event that sort of brought computing to each one of our doorstep was the World Wide Web. So Berners-Lee, in sort of a sequence of steps in '89, sort of built the technology, of what it meant to have this connected ability to view pages and other places. And then in '93, made the radical decision to do it non-commercial. The World Wide Web succeeded because the code that he developed and the platform that he just simply distributed. And as a result, we all use it today and have that kind of impact. But the World Wide Web, in some sense, wouldn't have had the impact that it did unless we could know it was out there. And that was really an effect of the academics behind Google coming up with PageRank, and parallel to that, John Kleinberg here at Cornell had his own advances that had the opportunity to make web pages searchable. And all of a sudden the web went from being an artifact that could be used by a few to an artifact that literally transformed our lives. And then as I think about data science, there are really two influential thought papers. There's a paper of Bryman, which talked about two cultures of, as we think about data science, of how much of statistics is based on understanding a probabilistic view of modeling reality versus how much is driven by computational needs. And it's really the two cultures coming together that cemented and were formative for the launch of data science. And this was brought home even further in a recent paper. So that's AI and data science, broad level, and a brief history. But let me say a few words about what machine learning is. So if you think about traditional computer science, well, there's an old computer, and it took data, and it processed it and produced output. Well, it didn't process it on its own. You needed a program to process it. And programs took data, and data had to be collected from somewhere, like maybe a brain scan. And of course, programs didn't come on. You needed a programmer who struggled, and still to this day struggles, to actually achieve the desired goal of taking the data and the program and producing the output you want. So that's a traditional view of what CS is about. Machine learning, on the other hand, is a complementary process. Imagine starting with data, and in some sense the output, and now you're going to produce the program. That sounds a little puzzling. So, well, the two would go hand in hand. If I could do that, then that could be the program that I feed into the traditional CS model. So what do I say data and output? That it really is a question of dividing the process of building the system in two phases. There's a training phase and a testing phase. That there may be a suite of data that I can use to train that aren't just data, but it tells me the answer in advance. I know what the outcomes are, and then I use that corpus in order to make the program work on the subsequent things that I want to actually use. So that's the framework when we think about machine learning. And one of the things that happened over the last 20 years, from when machine learning first got its start to today, is the scale at which we do training and the sophistication of the kinds of objects and entities that can be trained have become much more sophisticated. Starting with millions and millions of pre-labeled data is now the standard. And how you get that and what that means, these are all interesting and important questions, but it really frames the thing. So, formally, and you can see this is, dating back to '97. This is old. A computer program A is said to learn from experience E with respect to some class of task T and performance measure P if its performance at task T is measured by P improves with experience. Wow. Okay. Algorithms that improve on some task with experience. Okay. So that's a framing for what's meant by machine learning. And that is really driving both what's moving ahead in artificial intelligence and in data science. Okay. And there have been a number of big successes of the machine learning, again, happening in the background steadily for years. IBM's played a big role in this. That Backgammon was one of the first real successes. It's sort of a complicated enough game, but simple enough to gain things. And the way you could actually gain labeled data, outcomes of what works and what doesn't, is you could have the computer play against itself. And so by repeatedly playing and seeing from both sides which strategies were winning how, you could understand, put more weight on strategies that worked well and put less weight on strategies that worked poorly, and thereby achieve this level of sophistication. So this was a huge success. The algorithm taught itself how to play well. And of course, the bigger success and the more sort of shocking success was 3 years later when Deep Blue beat Kasparov. Okay. And this really sort of said machine learning is here. But notice, this is 20 years ago. That these foundations were all set, and what's happened is we've gone from a very artificial controlled environment to thinking about the impact on a much broader range of settings. Another space where you all have learned from this sort of algorithms that learn from itself and now learn on a personalized basis is what happens with your email. This is my inbox. And indeed, we all have this thing called junk email. And it is a machine learning algorithm that's personalized to us that learns from how we're handling email to know that this read and reply urgent message should end up in my junk email box. And we all know that while it's good, it's not perfect, right? So that's another important thing to think about. So all these things are in the air. That there's some confluence that's happening. 3 billboards outside San Francisco, California. And these are real billboards as you drive around. Call IDUS Cloud, sales management performance. NetSuite, the #1 cloud ERP, enterprise resource planning for startups. Brighterion, artificial intelligence and machine learning. The world is ablaze with the transformation that these technologies are having on this impact on our commercial lives. So why now? So in some sense, I think there are 3 elements that have come together at this point in time. One is Moore's Law. And I'll say a little bit more about it, but it's really captured by the growth in the speed of our ability to process that has consistently and steadily grown in an astounding way. The second element is the cloud is our friend. The notion of a compute cloud has changed the way and the opportunities for the entry, removing the barriers to entry of computing at scale for any enterprise. And this has just really been transformative. And then there's been this technological boost to this tradition of machine learning under the guise of the name is deep learning. And I'll give you a 3-minute tutorial later there. But all of a sudden, the level of advances and the ease of making them has taken a paradigm shift forward. And that's going to be another element as well. So that's how I'm thinking of the 3 elements of what just happened. Moore's Law. So there are all these graphs. What is Moore's Law? Well, in its formal, clear, initial sense, I mean, computers at their core have these things called integrated circuits that are actually the basis of the running. And back in the day, really back in the day, this is before my day, when Shockley got us all started, there was this transistor at Bell Labs, and the question of how many transistors you could put on a chip. Well, now there are various things that play the role of transistors in a very different way, but Moore, in a classic paper in '65, said that the number of transistors on a chip doubles every year, 2 years, 18 months, depends on. And the one thing I want you to take away from the graph below, I know that beyond the first row you can't read a thing, but you've got sort of the axis on the bottom is time. The axis on the vertical is the number of transistors in a log scale. Every nick up we double the number of transistors, and what you're seeing is a straight, flat line. Straight, flat line, when the vertical axis goes on what I call a log scale, that it doubles, is what literally is exponential growth. Yes, exponential growth gets used as a common parlance in a number of ways. This is the real thing. Okay, so this is exponential growth, and it's still happening. Now, that's the classic version of Moore's law. One can also take a more liberal view, that effectively computation speed or computational power to do how much in a limited amount of time is increasing at that rate. And that allows us to sort of project that things are going forward, because while transistors on a chip are there's some concern, and we've heard this. You know, I had my first conversation about that Moore's law can't really continue with another computer scientist that I went to high school with. We were sitting in his apartment. No, we were sitting in his dorm room at MIT in 1980. And you know, we told, well, there's theorems in that, you know, the speed of light is going to propose some limitations and blah, blah, but we're not going to hit that for how long? You know, it's what, 2018? You know, but there's still some sense that in the pure on-a-chip definition that there is some flattening. But what's happening is the extent that we all know about multi-core computers, even for the things that's sitting on our desk, and all of a sudden this world of parallelism of multi-core machines is sort of helping us take over and continue and pick up this sort of other version of Moore's law. And then there's another element that formerly is actually called Kreider's law, but I'll think of that as Moore's law of big data. That the amount of, well, if you sort of think about a classic computer as the one that's sitting over there and driving there, there's a thing called a hard drive that's on every computer, and how much stuff can get stored on a hard drive is also increasing at this literally exponential rate. That's what the left graph said. Parallel to that, the cost per unit of storage is going down inverse to that. And this is an amazing financial driver. But in some sense, this is now a war between capacity and need, because the amount of stuff that gets created is also growing exponentially, at least in the short term. And the base of that exponential seems to be higher than the rate at which. Now, whether this catches up, where we do this, we'll see. But it's sort of an interesting point in time. But you know, there are YouTube rates. Billions of pictures get uploaded every day. I mean, just think about all of those snapshots of food. Anyway. So another thing to bear in mind is that the world has become connected in an interesting way. And I mentioned in the brief history of data science that the emergence of the World Wide Web was really a transformative event, because rather than computing locally, everyone started computing globally. And the sense that we could cope with this was untested. So here is an abstraction of the World Wide Web. Each of those little blue circles, think of that as a web page. Okay? So that's one web page that, you know, maybe your home page, the home page of your company, home page of your department. Those arrows are meant to reflect links on your home page, or whatever page, to another World Wide Web page. So if you're, you know, you have a pointer to the staff in your department, and there's a link to each of your staff members, that would be then the 3 pages for that. So this gives us a structure. It's what we technically call a graph. I know it's not like the kind of graphs you grew up with, but it's the kind of graphs I grew up with. You can call them networks instead. So one of the things that happened when the World Wide Web blossomed, and indeed it blossomed in a fantastic way, that within a few years of Berners-Lee putting things up, again because of the non-commercial aspect, there were millions and millions of web pages that were individually posted that there was this need, of course, to be able to find what's out there. And the first real success was a product made by a now defunct computer company, Digital Equipment Corporation, which used to produce computers, was its main thing before it went bankrupt. But one of the things that it did in its dying days was it produced the first truly useful search engine, something called Alta Vista. I'm just curious. I want to know, who in this room, if anyone, used Alta Vista? Ah, wow, that's good. Okay, good. Now, the way Alta Vista created it is an object called a crawler. So what got coded was the ability to trace the existence of everything out there by one page following the other, and thereby figuring out in an automatic way what this graph looked like. And this was a radical idea in and of itself. And then the question was building the algorithms to be able to work with that. Now, I started life as a theoretical computer scientist. I studied graphs, I studied graph algorithms, and we always talked about asymptotic growth, and we talked about graphs at scale. You know, at that point, a big graph was 1,000 nodes. I am sure that if someone told me I should be thinking really, and not just about writing papers, about graphs that had 1 billion nodes, I would have said they were joking. Unquestionably. That just the scale didn't occur. But all of a sudden, we were confronted with graphs that, okay, at that point only had maybe tens of millions of nodes, but it was very clear, given the trajectory, that was the path we were on. And the next transformative step was this piece of trying to get better search algorithms by doing more sophisticated things with what a web crawler did. And that was the whole underlying principle of Google and of its PageRank and hits. In using this more sophisticated tools, I won't go into it, it somehow enabled us to get a probability distribution underlying all of this. But what the details are is unimportant. But we were doing a more sophisticated computation where the input to that computation was the web graph. And in fact, that computation, in formal terms, was, and now I might frighten people from some last math course they were computing eigenvalues of matrices that are, you know, tens of millions of rows and tens of millions of columns. And we were actually approximately computing these things. And so this was doing scientific computation, if you will, at a scale and a level of having an impact on practice that previous to that was unimaginable. Not because we tried and failed, we just never tried. And this gave rise to a range of things that we could start thinking about analogs of things that we could do at small scale to do approximately at large scale that has given rise to a good chunk of algorithmic computer science in the intervening 20 years. So this was really a formative event in things going forward. And you know, we all now probably seen images like this of the web graph, of what it means. And all of a sudden we've gone from thinking about computers and studying sort of a mathematical object to almost a kind of natural science kind of thing. This is, in some sense, a living, breathing object that is produced as an artifact of society that evolves and now can be studied in a natural science discovery kind of paradigm of creating experiments and trying to understand what its properties are. So this also fuels a lot of science today. Okay, so that was item one. Moore's law and the ability to there. That's another piece of why now. So the cloud is our friend. So again, the introduction of the World Wide Web created a new need. Computer networks are good, but for me to be able to access the web page of the New York Times from any machine almost anywhere in the world, certain countries not accepting, of course, actually required some amount of general proximity in terms of making the functionality truly effective. And so this gave rise to an architecture where underlying making web search and using the web in a stable way, and because it was part of the global economy, the notion of having server farms that were able to handle local traffic started building up the systems infrastructure that gave us capacity to handle computation at scale. But once having built this system infrastructure, it could be used for other purposes. Of course, the commercialization of the web and the digital economy worked as a big driver. But now, in addition, these were compute servers in addition to playing the role for the web. And because of the nature of the evolution of the systems meant to build it, you as an individual user, and Amazon was really the company that led the way in charting a market for this, can buy computation time anywhere at scale. And it's not just a mom and pop thing or a little small researcher in computer science or who wants to have access. If you look at modern commercial entities, even at the scale they think of, a company like Lyft or Uber gets its compute power not by building that internally, but by relying on the fact that there is this infrastructure out there to do that. So the unicorns are relying just as much on this infrastructure as everyone else. And so this gave this confluence of power that was really transformative. And then there was this third element, deep learning. And I'll come back to this towards the end when I've lost you anyway, and give you a quick overview of what that means. But for now, just think of it as machine learning on steroids, okay? So those are the three elements of sort of why now. Questions before I sort of transition? So let me give you a brief sense of how machine learning, ML, works. So we start out with the real world, and from that we extract data. And then the question is, well, how do I represent that data? So for each entity, I'm capturing and characterizing that entity somehow. Mathematically, I'm capturing it by a vector. Oh, gee, what's a vector? It's just a sequence of numbers, don't worry. Okay, it's a vector. And the key thing to think about it is, it's what we call a high-dimensional vector. There are a lot of numbers. So that doesn't seem any. Let me make it concrete. Let's talk about images. Okay? So in my spare time, I actually manage logistics for bike sharing, which is why I use that picture. So imagine a picture you've taken with your iPhone. And one thing that you're all come familiar with in digital technology is, how good is that camera? Well, one metric of how good that camera is, how many megapixels the images you take are. So let's say 12 megapixels. So what does that mean? Well, what that means is as I look at that picture, I want you to think about that as 3,000 rows and 4,000 columns. Okay. So altogether, multiplying, 3,000 times 4,000, assuming I did it right, that comes out to be 12 million. So there are 12 million little tiny pieces of that picture. And if I look at that picture, as you sort of, at that level of granularity, the picture's pretty much constant. So it's one color, one intensity in that tiny little speck. So I can capture that speck by a value. And how many binary digits, because computers just store things in zeros and ones, it takes, well, 24, kind of typical is how a color image might be captured. But that's what we do. So I've now transformed an entity, an object, a picture, into a vector that's 12 million numbers long. So that's the image. Okay. And now it's just a value. It's just a series of values. And now we can start processing it. And now you sort of see, and of course maybe I want to do something called image compression, and we've all used some image compression tools. You know, when you send that picture on your phone, it gives you the chance of you know, real thing, large, medium, small, invisible, and, you know, but that gives you a sense of scale, right? You know, one image, you know, is huge. Take another example, and this is sort of, maybe many of you have heard of what the Netflix challenge. So what was that all about? Was that, again, imagine a very big table. Now, as I think about rows, each of them corresponds to a person on Earth. No, a billion or so, a few billion. Every column corresponds to a movie. Okay. Every entry, so what I think about Casablanca, which is probably not visible at the back either, that was the movie, I give it a 10. Okay? So that's my rating. So if you think about Casablanca and what everybody thinks about it, now we have, you know, however many people we're imagining in the database, number of entries of how people view that. It's a vector. It's a point. Okay. So at the baseline, before we get into machine learning, there is sort of something that's known as unsupervised learning. So imagine, instead of it being a vector of length 12 million, we'll take a simpler case. We have a vector of 2, okay? So we have a 2-dimensional vector. So in this case, it's the x direction and the y direction. You know, you all remember 8th grade math, hopefully. So here we have a representation of some number of vectors, 2-dimensional points, that might represent things. And we might want to just understand what movies are like each other. What clustering can we detect as we look at the space of all entities there are? So you might say that those sort of are natural. I mean, the human eye is great at this, right? So you might say that those are clusters. And notice that I didn't capture everything in a cluster. That, you know, that there are those 4 points that I didn't put. Those are sometimes called outliers or anomalies. And so detecting them as part of the process is sort of an inherent element. But we're characterizing this group of vectors, 2-dimensional points, by this kind of grouping. And we're learning about how to classify these groups in a purely automatic way. Okay? But no human in the loop, no labeled data. This is just transforming what we got into some sort of understanding. And that's why we call it unsupervised learning. Now, the brain is pretty good about doing this in 2 dimensions. You'll be surprised, or maybe you wouldn't be surprised, how bad you are at it, even if I tried to give you a very good tool for representing 3-dimensional data. And remember, the data now is in the, I mean, whatever it means to visualize, millions of dimensions. Okay? So having the tools in order to do this, again, and these kinds of questions evolved in you know, a context of smaller dimensions and understanding these kinds of questions, but at much smaller scales. And again, the magic and the lesson from the paradigm shift of Google search was that we can think about approximate versions of these kinds of techniques working at scale. And in some sense, we also move to thinking about the learning problem as a kind of optimization problem. As you, I'll go back, as you sort of think about those ovals, what I was doing was thinking about a relatively limited amount of measure. I had sort of learned where they were centered, how many there were, how elongated they are in each direction, maybe how rotated they are, and which points I'm going to throw away. I'm going to just say I'm going to count them as outliers. That these are different parameters that I need to learn in order to do that. And then the thing is, let's frame this as a optimization problem in the sense that I have some metric for evaluating a particular way of doing that. And now I want to find the best parameters that capture the thing. That it wasn't that those circles, were much bigger than the points that it contained, that there weren't too many points out, that there weren't too many circles. So the kinds of characteristics that we want. So now I've characterized the way I've clustered it, again, by a certain set of values in a smaller dimensional space. And so I end up with surfaces of solutions. And for each surface, now I want you to think about the height in these three-dimensional plots as the quality, or the badness, let's say, as higher it is being bad, of that solution. And so what I want to do is I want to find a low point on this surface. So now the question of learning becomes an optimization problem, and I need a technique for doing that. And the two problems, left and right, are characteristically very different. Technically, the one on the left is a convex optimization problem. And that basically means that I just do hill climbing, or in this case, valley descending, and I can end up with something that is really the best. But if I think about doing that for the picture on the right, I may end up with a very high valley when there are much deeper valleys not so far away. So the bad news is that many of the learning problems that we confront are of the right kind, not the left kind. And a lot of what's going on is trying to figure out methods that allow us to optimize over the kinds of surfaces that come out on the right. Okay? And when we talk about a lot of the research that's driving figuring out how to make deep learning even better, much of it is exactly how do I phrase the optimization question right so that the surface is relatively good and that I can do interesting things in terms of that surface. I talked about the Netflix challenge, but they actually had a bigger, a more forecasting kind of goal. That of course, everybody hasn't watched every movie. And the goal now is a question of inference. I haven't seen the Maltese Falcon. No, I really have. What would my writing be? And the fact that those are clustered close allows us to give information. Okay? So giving you a sense of how the kind of information we do allows us to extend to that kind of domain. Now, a number of tools are coming into play in order to make all of this work. In one area, what comes generally under the name of natural language processing. And this consists of many pieces, many sub-pieces. And again, Martha set the stage for me perfectly. I mean, she's been working on this for since decades ago. So this is a slow and steady evolution, and it comes in various things. Automatic speech recognition, and the text in the picture right says that we've gotten a lot better at it, but there's still things to do there. The other way, go from text to speech. I mean, we all know that the automat on the end of the phone line is a bit more human than it was there, but Waze still thinks that trip hammer is pronounced trip hammer. Why? Comments. And Google Translate works really well on a menu in a foreign language. But the email from your colleague that was going to another colleague that was in a different language, or in this case, let's say from my wife to her brother, not so good. Okay. But it's gone a long way. And exactly this is sort of where the frontiers are there. How you extract information and structure, all of these are questions of natural language and natural language processing. One important thing, just to give you a sense of the subtleties, is one area is something known as sentiment analysis. And this is, clearly, consider, you're given a review, let's say, of a restaurant. And you want to know, is it positive? Is it a positive review? And to give you a sense of the subtlety that's involved here, consider the following 4 sentences. It was a great restaurant. You all know that's positive. It should have been a great restaurant. Maybe not so positive. The restaurant was great in that it will make all future meals seem more delicious. Despite the pleasant experience, I can support the many reviews that it was a great restaurant. Okay. So you see the subtlety of, just the mere words alone aren't what generates the sentiment. And of course, it didn't hurt that I was inflecting it as I was saying it. But there is all this that comes in. And the picture you really can see was meant to sort of say that part of what goes underneath is also understanding of the grammatical structure that interplays with the word structure and how that actually can be done. But again, this is a domain in which machine learning has had huge impact. Okay, I'm coming towards the end of the time, so now I'm really ready to blow you all away. I'm going to give you a 3-minute introduction to deep learning, because I know you've heard it out there, and there. Here we go. So at the core of deep learning is an artifact actually created here at Cornell of a perceptron. Rosenblatt was a PhD student at Cornell and was later on the faculty. A perceptron. So again, now imagine that I'm back in my email filter, and I want to separate spam from genuine email. Okay, so red is spam, blue is there. And let's say I want to draw a line that does it. Well, in this case, if I squeeze hard enough, I get a line that puts all of the red on one side and there. But it's clear, I'm barely getting by. And lines, from 8th grade math, y equals ax plus b. Now, don't forget, I'm not working in x and y in 2 dimensions. I'm working in millions of dimensions. So there is another analogous representation, but we call them hyperplanes, but don't worry, they're lines. There's a representation that gives us that. So that was a perceptron, and that we could characterize what it was doing in this sort of simple way. We had its input, the coordinates of that vector, and a constant, and we generated an output. Well, we could actually then go to a multi-layer perceptron, which takes that input and then puts different weights and creates a hidden layer of sub-pieces, which then get done with this line. And this mixing that happens has a particular structure that Rosenblatt, which were called rectifier linear units. They're sometimes called hinge functions now. It doesn't really matter what they are. And this allowed, even with the sort of expanded space, it didn't, got better when you expanded the space of and then you go into hidden layers, not just one layer, but many layers, and you're building this structure. And you're saying that all of this is going, and I drove that by doing this more complicated thing, rather than just in the line space, we now have sort of more sophisticated ways that we can do it. But the takeaway that I want you to learn is, remember what I did with the ovals? That I had an optimization problem that learned the parameters of what those ovals were? I now have to learn all of the parameters of this structure. And the way I'm going to do that is this notion of supervised learning, which trains based on knowing what the answer should be for lots of initial points. And when I say lots, I mean millions that I want to infer as a basis that I get a set. So I go from, just as I had this unsupervised learning, I know all of the answers, but I now need to compute all of these parameters. Now I'm going to use that in the future. Deep learning works. One of the real mysteries is why. I barely go through a week without seeing a new paper or a new talk of someone trying to set a framework. Why deep learning works. There are ideas, there are things, and there are certainly ways to try to push deep learning further. But you learn this year, last couple of years, AlphaGo was sort of the, you hear TensorFlow and Google in its cloud computing is putting TensorFlow into the cloud and making that available. These are all the things that are percolating here. So one last vignette, and then I'll stop for questions. So this is a demo that my colleague Killian Weinberger in computer science has to give you some sense of the power of all this in sort of a very tangible way. And the point is that, remember we started with images? We had a way of representing them. They're all in some space. And here are 7 images. So we're going to sort of learn what that space looks like and how images of faces look like. Okay. So that's what's learned. And let's say what we're trying to learn is the classification between people who are bearded and people who aren't. And let's just build this into the structure of the network. And there's Killian, and not bearded. But they're embedding in this space and this separation between what's bearded and what's not. There's therefore also a translation of what it takes to go from being clean-shaven to being bearded. So then we could ask the question that if I think about all of this and I put Killian in and I think about what happens when I move him over, and I want to move him from the source of clean-shaven to a target of, what emerges? Bearded Killian Weinberger. And this is technically what happens. This is the mathematics underneath it that has allowed it. We're just using our understanding of the structure of the space so as to make this kind of transformation. Okay. Now this is a playful toy application. Well, maybe not. Maybe you care about what you would look like if you had a beard. But the last thing I want to touch on is sort of my own perspective on sort of why I think there are great potentials within alumni affairs and development. And one thing that separates college, university, alumni affairs and development from most entities is you owned the data for these individuals at the formative times of their lives. You know what organizations they were in, you know what fraternities they were in, you know where they lived, you even know their roommates. And this web structure, this network structure, is something that we've gotten very good at exploiting as we develop these things. So you know a much better version of their social network than Facebook does. Facebook has a bad approximation from their current interactions. But the corpus of knowledge that university information systems have give you a way of having far more usable information in an interesting way. And of course, the other key thing is everything is in terms of features. Right? So you, again, by having not just tracked them since they graduated, but knowing about their lives there, you have a range of ways in which you can extract the information that's valuable to you. So that's just sort of one piece. Whoop. But of course, the last message I want to close with is that these are just tools to help us do things more effectively. And yeah, Martha mentioned that she believes that one thing that can take humans out as autonomous driving. But even that, I mean, they're only thinking about relatively controlled settings. But whenever a technology and a set of tools gets introduced, you essentially start with cruise control, right? Something that helps you take off the mindless things and does things better than you could do. You know, we can't all keep our speedometer at 62 miles an hour. But cruise control can, right? So this gives us, and that's the analog that I want you to think about as these kinds of tools can become part of our lives. But there's so much we don't understand. That algorithms making decisions, what does it mean for an algorithm to be fair? Can we make algorithms fair? Or how do we, what kinds of biases do we introduce by having algorithms at the core of our decision making? And this is current research. A lot of it, very interesting stuff going on here at Cornell. But the bottom line is that whenever artificial intelligence gets introduced in a domain, we better do it intelligently. And with that, I'll take questions.
So is there a correlation between the depth of learning and what we understand as the largeness of data or the variability of data and so forth? So for example, if you have a database which is an alumni affairs database that has events data, volunteer data, solicitation data, giving histories and so forth, is that a sufficient data space or feature space or dimensional space or volume space to be able to characterize the intrinsic nature of an individual, which is really what they value in the world? And so I'm wondering about your thoughts on that. And then obviously there's the whole question about who owns the data and those things like that. But really the first question is I'm thinking of.
So I told you my answer was going to be I don't know.
Okay.
And indeed the honest answer is I don't know. That for every domain, as these tools are coming online, the question is that training data. How rich does that have to be in order to be a good predictor of things you don't know yet? Now, you also do, in some sense, if you trained things on everything up to last year, then you can have training data that emerges by what did happen for the cases that you did various activities last year. Whether that will end up being sufficient, the only thing I do is these are the experiments that are going on across a wide range of disciplines, and the tools are getting better every year in dramatic ways. But whether the technology is enough to do it at the scale that you actually have, with the feature space that you have, and what the right feature space is, if it isn't now, my bet is it will be in 5 or 10 years, just because the rate at which and the range of different applications that there. But I mean, there's sort of it goes back to that original slide that I talked about what AI is, that the questions get framed like, well, your brain has how many synapses and how many neurons, and it's really took the fact that we're at the level of a brain in order that we can actually do it. I can't say I mean, it's a good analogy to draw, but is it really the science that is it just that we happen to have the right algorithms that kick in? And after all, we know that there are other species that have different characteristics for their brains, and yet do decision making in interesting ways that with the same number of, same simplicity of nets that are getting designed, we can't make simple decisions with. So, I mean, to give you some perspective of how far things work, I think it certainly was within the last 15 years that I've been at a research frontier talk, where we're shown a collection of images and which ones are dogs, and the error rate is something of 20–30%. So the rate of progress has really been substantial. Yeah, that'll drive it.
Hello. The question that I have goes to, you've shown us a lot of advances in artificial intelligence and things that man has accomplished to do with it. I wonder if it's as important to reflect on and look at things that it might never be able to do for us, or to think about that there's learning that man does that computers could never do through the eyes, smell, taste, sounds, and to pull all those things together and see things that computers could never see. I'm wondering if there's some things there that should also be considered. Thank you.
It's a great point. I mean, again, notice that I made this dichotomy of, are we trying to simulate humans, or are we just trying to match their output? So actually, for the examples you give, computers can smell and see and hear and taste. Well, maybe not taste. Taste may be tough. But those are all captured by sensors and signals and can be converted to digital output. I mean, the music that you listen to on your phone is nothing more than a sequence of digital bits. So, I mean, or any sound can be, so computers can hear in their own way, right? So it's a question of the input is, this is the digital transformation of societal output. And so how we can do that. Now, it's not going to use the information in the same way that you or I did, but can we build models that create responses that are similar? The experiences so far we can. Now, will we learn that there are? I'm sure there are going to be impediments. Thinking about thinking. At some level, it's but it's scary. I mean, there are very well technically trained people who foresee all kinds of scary consequences of what it means to create machines that think. And there are, I'm sure there are limits, but I wouldn't want to have to place any money on what they are.
So we're at time now, so if we could wrap up. David, thank you so much.
I'll hang around for the break, so if people have questions that they weren't able to ask, please come up and talk.
That sounds great. That was exactly what we were hoping to get to start this day off, and thank you so much for sharing your expertise with us. And there's now a 15-minute break, and we will start our panel at 11.